Okay. Oh, Ron's here. Awesome.
Hi.
Hey, Ron. Uh, so, Cynthia, should I start, or is that kind of a preview
Oh,
before
yeah.
we?
Oh, are we waiting? Who are we waiting for?
No one, I guess. We have full house. So Eric's here, Ron's here, Matt, you, Sudeep, Alex. Everyone's here actually. So Brandon's here as
Yeah.
well.
Awesome. Okay, yeah, you should totally get started. Go for it.
Awesome. Uh, so I believe you can see my slides and also hear me properly. With that assumption, today I'll be talking about my research work that focuses on accurate and interpretable causal inference for high-stakes decision making. And especially I'll be walking you through a case study about self-help groups, poverty trap, uh, risk tolerance. And all of the subjects are very personal to me, and that's why I kind of chose this example to introduce you to our work that we are working on. So the story starts somewhere in 2015 winter when I was visiting a village in central India. And I was hosted by this very charming young fellow, and he offered me a fruit. I was eating that fruit that he offered me. And during the conversation, I realized that his father had died of starvation a few months ago. I was kind of very sad and curious what happened. He told me a few years ago there was heavy rain and flooding, which kind of led to bad crop here because he was fairly small farmer. No bank or financial corporation would give him insurance or loan to kind of allow him to cope up with the losses. So he went ahead and borrowed from a local money lender. And often this money lender gives you credit at really high interest rate, somewhere around 100%, right? Note that he needed this money to survive. And it was practically impossible for him to pay back without further depleting his capital. So this misery eventually led to a situation where he couldn't feed for his family, leading to his father dying of starvation. So this is a classic case of poverty trap where you are already poor and hence you cannot access the resources to grow, further leading to a worse outcome. And this is sadly the reality for a large size of population in developing countries like India. Many solutions have been proposed. Note, many solutions have been proposed and experimented with. And one of the idea is of the self-help group. I'll introduce you to the self-help group now. So self-help group is a community-based group of around 10 to 25 members. They're usually women from similar socioeconomic background, all voluntarily coming together to save small sums of money. So somewhere around like $5 to $10 a year on regular basis. They pool their resources to kind of become financially stable, taking loans from this collective saving in the times of emergency like floods or droughts. Also kind of borrowing money for important life events like a wedding or a purchase of asset like buying a cow or buying a few grains to sow in a particular year. And recently, under government mandate, the financial services offered to the self-help group have been collateral-free loans at a very low interest rate. So this is awesome because this kind of, if you're participating in this, then it kind of allows you to access the banks or non-banking financial corporations at a fairly low cost and may allow to kind of come out of poverty trap. So that's the exact question we are trying to answer today. With all these promises, does participating in a self-help group increases one's financial risk tolerance? Right. So the way we measure this is that if a unit has an active loan from a bank or from a non-banking financial corporation, then we use that as a surrogate measure for the financial risk tolerance. That is, having an active loan is good. It is an indicator that a unit has access to formal financial instruments and that it can borrow the money from them, and the borrower and the financial institutions also trusts the borrower, right? So so let's look at the difference of participants versus non-participants and how many of them have loans. And the population of our interest are people in this village in south of India, in the state of Karnataka. And so in that population, 63% of participants had active loans, while in the non-participant population, 75% had. Now, of course, you will say that there is this negative correlation between you participating in an SHG and active loans, right? Does this really translate to it decreasing your chances to actually get the loan? Someone might argue that people who participate in SHG are poor, and poor people tend to get lesser loans in general because of the reasons I mentioned before, and hence this negative correlation that you see over here, right? So the actual question we should rather be looking at would be, what would the participants' outcome be if they hadn't participated, right? So in the data that I was looking, this data was collected by Banerjee, Duffalo, and folks at JPL. And in the data I was looking at, so if you wouldn't have participated, your counterfactual would be 1.5%. So you can clearly see that there is an increase, right? And so I'm going to now introduce you to the methods, how you can estimate this counterfactual and all, but you can kind of see the contrast between correlation and causation here. And while you're making decisions, you should actually look at this causal effect, or you should do this counterfactual analysis to make decisions rather than just look at the correlation, because it might not be very informative of what's going on. A brief pause for questions about self-help group if anyone has, otherwise I can jump forward. I assume silence as I'm super clear. Amazing. Okay, so we kind of assume in this binary treatment case, so binary treatment in the sense either you're participant in a self-help group or you're not participating, right? So there are two treatment choices, 1 and 0. And for any unit I, we assume there are two potential outcomes. Y1 is the outcome if unit is participating in the group, and Y0 is the outcome if the unit is not participating in the self-help group, corresponding to each treatment choice, right? And the treatment effect is basically the difference between these two potential outcomes, Y1 minus Y0. It's a very standard causal inference setup. Of course, you can have different versions of treatment effect. We are just looking at we are just looking at the difference of potential outcomes as our treatment effect, right? There is a slight problem here, or there is a slight challenge here, and it is that for every unit, you essentially observe one of the potential outcomes because you observe one of the treatment choice. Either the unit is in a self-help group or isn't in a self-help group. You can't observe both of the potential outcomes, right? So let's say unit I was in a self-help group. So then your yi, which is the observed outcome, is equal to y1 or yi1, while yi0 is not observed, and it's sort of impossible to observe it, and hence it's impossible to know the true causal effect. Cool, that's challenging. So in that case, causal inference is sort of similar to a missing data problem, as Don Rubin says. But we can try to reconstruct the missing potential outcome using some statistical jugglery, right? And this is the basic idea of any causal inference method, because causal inference is a missing data problem. All the statistical jugglery that I'm going to show you today is primarily to estimate what would have happened if this folks hadn't participated, or what would have happened if this folks had participated. So that's the underlying big picture of causal inference. Randomized controlled trials, as you might have heard in context of vaccination, have been used since like 17th century to do the same, and have been considered gold standard. So in like randomized control trials, the randomization step in itself is very crucial because it allows you to break the correlation between the treatment and the pre-treatment covariates. Remember, I just told that poverty can lead to you participating in self-help groups. So there is a correlation, there is a causation or association link between poverty and you participating in self-help group. You somehow want to break that link. So the randomization step in RCT allows you to do that. And then now you can look at the naive difference of outcomes between the control and the treatment group and say this is the causal effect. So this is the big picture idea of RCTs, right? But what if you can't do RCTs? What if RCTs are costly, or under some situations it's kind of tricky? So many approaches have been developed to kind of estimate causal effects on observational data. So data where you haven't, it's not coming from an experiment. So where conducting RCT might be challenging. And the basic idea is kind of to control for the confounders. Confounders are kind of variables which naively, so to speak, affect both the treatment choice and the outcome. So you want to control for them. And by controlling for them, you're trying to recreate this pseudo randomized controlled kind of scenario under some very nice assumptions, right? So the kind of three main approaches, two are very popular and kind of I looked at them very closely. So matching tries to create this like for like match groups and compares the outcomes inside the match groups. So you do matching on pre-treatment covariate. Here in this example, I'm showing this one-dimensional covariate X, and you kind of make this red boxes and compare unit inside this red boxes because they are similar to each other. All right, so this is the idea of matching. On the contrary, regression accounts for confounders by fitting a regression model for treated and control groups and looks at the difference of estimated potential outcomes, right? So the red lines over here are the fitted curves. And then for a particular X, you can look at the difference of estimated potential outcome. The third approach is weighting. Weighting is quite popular. In most of the cases, you kind of inversely weight the outcome by the probability of the selection in a particular treatment group. And that's the third most important causal inference method that is currently existing in the literature. Of course, there are a lot more, but mainly you can kind of fit things in the scheme of estimation. So are there any questions till this point? Cool. So our work primarily focuses on matching kind of methods. Why matching, right? It's a very natural question. Why matching? Matching because it's conceptually simple. It's like comparing likes with likes. Also, if you look at the adjustment procedure, it's more like an interpolation, unlike regression, which is clearly extrapolation, right? So it needs lesser assumptions. If we perform matching on covariates, right? So if you do some kind of exact matching or nearest neighbor matching, I'll use this words later as well. It's interpretable. You can make sense of why a unit was matched with another unit and why there is certain treatment effect. So it's very interpretable. Further, it facilitates sensitivity analysis for biases due to unobserved confounding. We won't be discussing this today, but surely is an interesting research direction, and we'll be happy to chat about it after the presentation. Sweet. However, matching does not come without its challenges, right? Let's take a toy example of 3 units, U1, U2, and U3. So unit U1 is treated, U2 and U3 are not, they are in control. Yeah, so let's say you decide to match on pre-treatment covariates, which is X1 and X2, occupation and toenail length. Let's say if you were matching very tightly on the toenail length, for instance, then you will match up ending unit U1 and U2, right? Because their toenail lengths are very similar. But let's say some other person comes who has domain knowledge about this field and says that, hey, don't match on toenail length, match on occupation. That makes more sense. right? Because their incomes are kind of connected to your occupation. So then if you match tightly on occupation, you end up matching U1 and U3. And this kind of changes the estimates that you have for treatment effect and eventually affects your inference, right? So this kind of potentially highlights that the choice of distance matrix is critical and can potentially alter the inference that you have. Because if you match U1 and U2, you said, oh, the treatment effect is nothing. They both have loans. Even if you participate in self-help group, there is no difference. While if you match U1 and U3, there is kind of a treatment effect. And so that kind of changes the inference. And so hence the choice of distance matrix is sort of super critical while you're doing matching. How do people conventionally do it? I mean, matching has been used for so many years. People should have figured this out, and they're using certain methods. So how do they conventionally do it? The best option that you have is match exactly, right? If you match 2 units exactly, there is nothing left to guessing. You're matching tightly on everything. However, it is statistically inefficient, right? Because you need a lot more units when you are matching exactly. Also, if you have continuous covariates, it's just impossible to match exactly. Cool. But if you have access to domain expert background knowledge, then you can ask them to design a distance matrix for you. You can say, ask them, is it more important to match an occupation or tonal length? And they can give you weights for it in some sense. And you can use that distance matrix. Awesome. But what if your data is really high dimensional? There is no reason for us to believe that domain experts might be able to optimally do it in a high dimensional scenario because it's just so complex. Okay. People have figured out kind of one-dimensional summaries of things to match on. So one of the things people match on is propensity score, which is your probability of being in treatment group 1 condition on the pre-treatment covariates X. The other is the conditional potential outcome under control, right? And the idea is that if you match on either of this, then it has those nice properties inside the match group that a randomized control trial has. So you can do that, and this is awesome. It just suffers from two very big problems which are close to us. One, it is not interpretable because this one-dimensional summary might not match likes with likes. It might match units which are different on covariates but similar on the score. Also, if your model of estimating the scores is misspecified, then you might get wrong estimates, and it might be a problem if it might not be really accurate. Your estimates not be accurate. Cool. People have also come up with something called genetic matching, where you use genetic algorithm to learn a distance matrix that ensures balancing between balancing, right? But the problem there is that it doesn't perform as well on estimating individualized treatment effects. It might kind of perform very well on an average, but if you are interested in conditional average treatment effects or individualized treatment effects, this might not be the optimal choice of matching method. Sweet. That kind of leaves us with this problem that nothing works. What do we do? And so we propose matching after learning to stretch framework, where we say, let's learn an interpretable distance matrix that allows us to match and create very tight match groups, and then perform gate estimation inside that. And we learn a distance matrix such that the irrelevant covariates are kind of weighted low, and the relevant covariates are weighted high. And I'm going to talk about what relevant and irrelevant means and what does weighting even mean over here. But I just want to pause for a second for questions for everything that I just talked about. Yeah. Sorry, I'm not able to see the chat. So if someone has posted questions in chat, I won't be able to see them. So feel free to voice them if. Cool. So I'll briefly talk about matching after learning to stretch framework, which learns at interpretable distance metric for nearest neighbor matching. Recall causal inference is the missing data. I just told you that. And we want to estimate, for the sake of generality, without loss of generality, y0 for a treated unit I. This is what we want to do. Right? We want to find an almost identical twin for unit I. So what do? We find pre-treatment covariates xi. Sorry, there was a question. Cool. So we find pre-treatment covariates xi, and then find xj, who is similar to unit I on. So xi and xj are very similar, right? But the good thing about j is that j has opposite treatment choice compared to unit I. So let's say unit I is treated, then j is in control. We can use unit j's potential outcome as the estimate for the missing potential outcome of unit I, because it has opposite treatment assignment, but xi and xj are very similar. So these two units are very similar. And my estimated treatment effect thus is going to be the difference of observed outcomes for yi and yj. Note that the word similar here is extremely loaded, as I just showed you. And we want to learn a distance metric that optimally estimates this potential outcomes, y0 and y1, and hence in turn estimate the treatment effect, right? Because my choice of what similar means affects what y0 I look at. And so I want to learn the word similar in an optimal way, such that it minimizes my error in estimating the potential outcomes. Sweet. So let's consider the objective that we are interested in. That is, we want to minimize the discrepancy between the true treatment effect tau I and the estimated treatment effect tau prime I. I just showed you what the estimated treatment effect looks like, so you can use that as an intuition for now. But of course, there is a problem that we do not know the true treatment effect. And so what do? We kind of open this up and by applying triangle inequality and say, okay, tau I minus tau prime I is definitely less than y1 I minus the estimated yi1. And it's plus yi0 and minus the estimated yi prime 0. Cool. Now, for treated units, we know the first term because we know the true y1. And for the units in control, we know the true y0. And so we can look at the second term, right? So what we can do is we can match unit I with unit j, who have same treatment assignment, and then use unit j's observed outcome as the estimated outcome for I, and then look at the discrepancy between both. That's our loss. We know we can do this because we know true y1i, and we can use yj as the estimate for y1i. That's the basic idea over here, and then we just sum it up over all the loss, and then we can minimize it, right? So that's exactly what I'm doing over here. So my estimate y prime t is basically this proportional to this weighted yj, where the weights, if you see, are inversely proportional to the distance, right? So if you're really far away from I in this X space, then you're weighted really low. You're not that important. I don't want your outcome to contribute in my estimate that much. But if you're really, really close to I, then I really want you to contribute in your outcome to contribute in my estimated outcome. So there is the distance in the weighting function. And so the loss for unit I is the difference in the observed outcome and the outcome estimated using this weighted nearest neighbors. And changing the distance matrix will change the weights for yj, for each of the yj's. And we want to find such an M opt that minimizes this cumulative loss. Is this clear? And if there are questions, I'm happy to take them.
Harsh, there is a question on chat.
Oh, I see. Thanks.
Yeah, I'm just asking. Is the loss function the same as violation of the consistency assumption?
So, what do you mean by violation of consistency assumption? Sorry.
Because by consistency assumption, it means the observed outcome should be the same as the potential outcome if the treatment is as observed. And
right.
You are minimizing the difference between these two.
Right. Yes, you're right. Yeah. So in some sense, yes, exactly. This is true under the assumption that if xi and xj are similar, as in if xi and xj are arbitrarily close, then yi1 and yj1 should be arbitrarily close. And so if I'm using yj as the estimate of yi for two units where xi and xj are close, then yi and yj should be also very close under that assumption. Yeah. Right, so this is exactly true. So this kind of takes me to the next slide, which is we use a specific form of distance matrix, which is the stretched Euclidean norm, right? So you all might be familiar with the Euclidean norm, the L2 norm. We're just kind of stretching the dimensions of L2 norm slightly differently. So M over here is a diagonal matrix, which stretches each dimension differently. And specifically, it learns a distance matrix which stretches the important covariates more, which are very important for determining the potential outcome, and compresses the unimportant ones, which are not really important for determining the potential outcome. So let's say if tonal lengths were not really important for determining if you get the loan or not, then it would really compress it and you would not be matching on it very tightly. But if income of a person or education of a person is really important, then you would kind of stretch it a lot and you would want to match very tightly on that. And note that we are choosing M as diagonal matrix here only for interpretability. You can choose any form of distance matrix pretty much over here, right? Nothing stopping you from that. So broadly speaking, the Maltz algorithm in a nutshell is that if you have a data D, you split this data set into beta random splits, and you use one of these splits as a training set and beta minus one of the splits as the estimation set. Use the training set to learn an interpretable distance matrix M opt, and then use the learned distance matrix to perform nearest neighbor matching. So for each unit in estimation set, form a match group. And then inside the match group, you can look at the difference of means or fit a regression inside the match group, whichever favorite estimation method you want to use to estimate conditional average treatment effects, conditional on the covariates that we had matched on, right? You can repeat this process by switching which set goes as the training set each of the time, right? So you can repeat this process beta times. And then just to avoid bias in your estimation or problems in estimation due to the splitting, the earlier split you did, you can repeat this whole procedure alpha times. So for each unit, you would have alpha times beta estimates of gates, and also you would have alpha times beta estimates of a distance matrix. It kind of allows you to get the uncertainty estimates on the distance matrix that you learned and also the gates that you are estimating. Sweet. So I kind of told you that Maltz is both, I claimed initially that we want something which is interpretable and accurate. I kind of justify what if it's really accurate and if it's really interpretable or not, right? So because now I'm talking about is Maltz accurate or not, I'll use a synthetic data experiment. The synthetic data generation method is kind of designed by us, but it's very common in the literature to use this DGP. The DGP is pretty straightforward. Your treatment choice, TI for unit I, is function of first two covariates of unit, xi0 and xi1. Your potential outcome under control is just a linear function of the pre-treatment covariates xi. Some of the A's might be 0, so that leads to irrelevant xi's and relevant xi's. So the units which have non-zero A's, AJs are relevant, and for units which have for covariates which have AJ equal to 0, those are irrelevant covariates, right? So it's a linear function. yi1 is the same linear function plus a linear causal effect and a quadratic causal effect, right? So note that even though this DGP is fairly simple and interpretable, it has nonlinear heterogeneous treatment effect, which is kind of challenging. And if we are looking at conditional average treatment effect, we want to recover this nonlinear heterogeneous treatment effect. That's what we are interested in. So in the plot on the left, on the y-axis, it's the relative error in estimating this conditional average treatment effect, or you can think of as individualized treatment effect, right? So that's the error in percentage. And on the x-axis, I'm showing what happens as I increase the size of the data set. So even for a fairly small data set with 256 units, right? Malls kind of performs on par with non-matching method like BART and Causal Forest. Kind of consistently does this as the size of the data set increases. Of course, propensity score method is not designed to do gate estimation. It's designed to do AT estimation. So we expect it to do bad. But even prognostic score matching is kind of not doing as good as malls. And this kind of highlights the importance of learning a distance matrix up front to do matching, so that you can have really tight match groups and do gate estimation in a fairly accurate way. Okay. Now that we know that malls on synthetic data performs on par with non-matching, highly flexible black box methods, is malls interpretable, right? Because that's the one thing which separates it from this black box methods. So I performed this analysis on the microfinance data set by Banerjee, Duflo, Matt Jackson, and others, collected from 2010 to 2012 and published in 2013. And what you're seeing here on x-axis is the different values of conditional average treatment effect, measured as the equation below. And the y-axis can be thought of as the probability density function, right? So what's the probability that someone would have treatment effect, let's say 1, and you can kind of look at the density function here. So this is the PDF, the estimated PDF. If the easiest way to look at it is estimated PDF. So you can kind of see that there is a spread, but it's kind of a unimodal distribution, and the mode of this distribution is somewhere around 1.25. The mean is around 1.39, right? But there is some sort of heterogeneity also in this distribution. And on an average, the participants gain by participating almost 3 times, right? Because their chances of getting loan increases 3 times. And how am I seeing 3 times? Is because e to the power, so this is log, right? So if I were to look at actual probability, it's e to the power whatever the mean is, and then subtract 1 from that. So that's the increase that I'm looking at. Okay, this is cool. I know that, I mean, this can also be done with other methods, right? What's so special about distribution of gates? Cool. If you want to know what was important to match on, what is the distance metric that you actually matched on? Was it important to match on education, or was it important to match on if you had savings account before participating in treatment effect or not, before participating in SHG or not? You can look at that, right? So the learn distance metric on average says that it's not really important to match an education. Maybe education is not the very outcome determining factor over here. Maybe if you had a savings account or not is a very important thing to match on. So match people who have savings account with people who have savings account, and match people who do not have savings account with people who do not have savings account. Also, you can see the variance of matching on cost is high. So we can say it is fairly important to match on cost, but we are not 100% sure if it's the best thing to match on. So you can kind of let go of a bit here, but it's important to match on ration card color, which is the surrogate for income, right? So people in India, there is this fear that they often might not report their income correctly. So you don't ask their income, you ask the color of the ration card, and it kind of tells which income bracket they are in. So the ration card color it's important to match on that because it shows income, and also gender. You should match females with females, males with males, but it's more important to match on savings. That's how you can read this plot. And lastly, if you are even more curious on going even more granular, then you can look at the match group. So let's look at unit 004, which is in control. So it's not participating in a self-help group. You want to know what would be the treatment effect for this unit, right? So this unit hasn't got the loan. It's female, they are female, aged around 18 and 12 years of education. They are matched with units who are around 21 and 22, so sort of same-ish age group. They also don't have savings account. As I just told you, it's very important to match on savings. One of them has same caste as the control unit of interest, but the other does not. Same income level and same gender, right? And here, this units, both of them are part of self-help group and both of them have loans. So you can say, I'm just showing a smaller size of match group, right? Because I can show 50 units over here or 15 units over here. So I'm just showing 2 of those units, but you can kind of fairly see that you can look at the units, they look fairly similar to the unit of interest, and you can also look at their outcomes and see, oh yeah, this makes sense. This is what's happening here. Just compare that with prognostic scores matched group, right? Because that's another matching method which is performing pretty good. Here, even though this unit is matched with unit 321 and 874, they do not really look very similar on the covariates. Maybe they have same conditional potential outcome, but they do not look really similar on the covariates. So in that sense, these are very interpretable because you can clearly look what the covariate values are and if it's important to match really tightly on them. And that's what you get, unlike prognostic score, which it doesn't really make sense why these units were matched together up straight away. So I'm just going to pause here for questions and let you stare at this figure for a while.
Yeah, 2 questions about the weights. So presumably you would have to do some sort of standardization, right?
Yeah, so you upprint, normalize. So that's a very good question. So there are 2 things here. So some of these units some of these covariates are discrete. So you need to treat them, you cannot do L2 distance on them. So you kind of do Hamming distance, weighted Hamming distance for them. And for other units, which are continuous, you normalize them by subtracting mean and dividing it by standard deviation for those units. So age and education, I kind of treat them as continuous, while savings, cost, ration card color, and gender, I treat them as discrete in this case. Does that answer the question, Ajinkya?
Yeah, that does. Thanks.
Sweet.
I have a question as well.
Mm-hmm.
So if we go back a slide, I guess the issue there could be like closely correlate. If you have 2 closely correlated things that you're matching with,
Mm-hmm.
then one of them could be very highly represented while the other one is, very low. Right?
So not really. So if let's say savings and ration card color are highly correlated, malls will ensure that the weights for both of them are high. So and the very fact that they are highly correlated and they go hand to hand, it doesn't really affect mal's loss function to kind of weight both of them high, right? Because you will eventually be matching anyways tightly on both of those covariates.
Okay, I don't 100% see why, but I can accept that.
Yeah, so it kind of goes back to how its optimization is done under the hood, but you can probably take my word for it that if two of the covariates are correlated and they both are important in determining the outcome, they both are given significant weights.
Okay.
Sweet, I'm just moving forward. So there are a lot of social scientists in this room, and they will complain that, hey, in developing economies, the financial wealth is not the only important thing. There is something called social capital, right? So if unit A is hungry and unit A does not have money to have food, unit B and C, which are their relatives or friends who might be slightly well off, they might end up helping unit A. And so unit A might never actually end up participating in a self-help group because there is a hidden self-help group or an implicit network effect going on there, where your social capital is actually helping you come out of poverty. And there is a paper in 2004 by Martin and folks, which says social capital is associated with decrease in risk of hunger. So whatever we showed here was kind of assuming that each unit is independent of each other. But what if they are in this social network or relational setup? What do you do then? Like how do you deal with relational data, right? And so my next work that I'm going to show you is kind of trying to solve this problem in part by allowing, so by defining a declarative framework and allowing users to represent background knowledge. So one of the background knowledge is that, hey, this social capital thing is important, is background knowledge. It allows you to represent such background knowledge and infer causal effect on relational data, right? So what do I mean by relational data, and like what are the challenges in the relational data that we are interested in? Is relational data is something like this. There are a bunch of tables of different things. So there are heterogeneous entities. There are 3 entities here: households, which are units, U1, U2, U3, self-help groups, S1, S2, and villages, right? So I don't have table for villages here, but you can have different kinds of entities at different levels. And these entities are in many-to-many relationships. So for example, unit U1 is participating in S1, U4 is participating in 2 self-help groups, S1 and S2, right? So they are in many-to-many relationships. There is also a social network between the households. So unit U1 is friends with U2, U2 is friends with U4, U4 is friends with U5, and right, so there is this network thing going around there. And this relational features, so features of my neighbors in this relational graph might be confounders. They might be affecting my choice of treatment and outcome, and we need to control for them, right? So those are the challenges with the relational data, and that's how the relational data, this is the kind of relational data we are interested in. Sweet. So what does Carl do in big picture? So Carl takes in a relational database like the bunch of tables I showed you. It also takes in the background knowledge from the user and a causal query of interest. And it reduces all of this thing into a single flat data table, on top of which you can use malls or any other favorite causal estimation method to estimate causal effects, right? So it's a way of reducing this complex data structure into a single flat table, which then is kind of more dealable with existing causal inference methods. That's the idea. And I'll go on each of this input in fairly depth, and also the algorithm. And feel free to interrupt me if you have any questions in there. So what does a relational database look like? I guess most of you are familiar with relational database, but the relational database has three things: entities, relationships, and attributes. Entities are something like a person U1 or a self-help group S1, right? These are entities. A relationship is something like U2 is friends with U4, or unit U1 is participating in self-help group S1. These are relationships. And attributes are, does U1 have a savings account or not? Or what is the capital accumulated by self-help group S1? These are all the attributes. And in this work, we kind of assume that the entities and the relationships are immutable. They're given to us and they're deterministic. They don't change. While the attributes are random variables, you can intervene on them and look at their effect on other attributes. So that's the basic assumption that we start with on our data. Okay, the major contribution in this work is the syntax and the semantics of allowing users to give background knowledge. So let's say I know that my income and my neighbor's income is going to affect my probability of participating in self-help group, right? So income is going to affect the participation probability. If I were to draw a DAG for that, it would be a very huge cumbersome DAG, because I have to write each and every unit and then map its arrow accordingly. Well, if I don't want to do and write a lifted representation, I can write in this way: income is affecting my participation probability. But this is incomplete because this arrow is conditional, right? This arrow is only if this unit is my friend or not. So the left-hand side representation is good schematically, but is incomplete. So what we kind of came up with is more data log types rules, which the user can input the information as. So let's say if the probability of me having savings account is the function of my income and my friend's income, I can write it as savings U is function of income of V, where either V is equal to U or U and V are friends, right? So you can kind of write this bunch of rules which are part of your background knowledge, and the algorithm will automatically generate the causal DAG in the background, which I'll go over. So this is the syntax by which you can input the background knowledge. The next thing you can ask is causal query, right? So in this simple example, you can have multiple kinds of causal queries. So each unit is participating in multiple self-help groups. So you can ask, what is the effect of me participating or a unit participating in more than k self-help groups on unit's outcome, which is loan over here. So in the simple example that we're going, we take k equal to 0, but you can have a different k. If your treatment was something else, you could have chosen a max, a mean, a min, a max, or at least one kind of qualifiers also in front of this the syntax, right? And so it's kind of fairly flexible in what kind of causal queries you can ask. Perfect. So now we have three things. We have relational database given by user, a background knowledge which is also given by user, and a causal query, and using our syntax for background knowledge and causal query. The next thing that our algorithm does is skeleton traversal. It kind of walks through the relational skeleton and maps it to the background knowledge, right? Because background knowledge has this nodes or rules which corresponds to columns or attributes in the relational database, and they are related, right? So we have also this where clause. So it does skeleton traversal. It performs something called grounding. So in background, it would construct this this complicated causal graph for you. You do not have to mention it. It constructs it for you. And the way it constructs is it walks through the relational database, looks where it fits in the background knowledge, and substitutes the variable for the observed value. Sweet. So now here we can say that savings of unit U2 is affected by its own savings and savings of and income of unit U1, right? So U1 and U2 are friends, and hence there is an arrow from income of U1 to savings of U2. Do not look and stare at this graph. It might make you dizzy. I do not recommend doing that. But the red line over here is basically saying that this is the causal query of our interest. We are interested in like looking and understanding what is the significance of this edge. The next thing it does is finding the confounder for our causal query. So it looks at the causal query. It says, oh yeah, I'm interested in understanding the effect of SHG participation on loan. It sees that for nodes SHD U2 S1 and loan U2, of the incomes of and savings of U2, and also the income on savings of U1, the highlighted nodes, are confounders. So we need to control for them. It traverses the causal graph and identifies this confounder which it wants to control for. Then it takes in the summary functions. So summary functions are something which we assume we know, and it allows us to construct a single flat table. So let's say we know that savings of U2 is affected by the average income of whoever it's connected with. So let's say one unit was connected with 3 neighbors and other had 5 neighbors. Then you want to construct a single flat table. You need to somehow collapse it to a fixed size vector. So you can look at the average income, and we assume that there are some nice properties about the summary functions, and then construct a table like this. So there's a column for the unit's income. There is a column for the summarized income of the neighbors. Similarly, there is a column for summarized savings of neighbors and their own savings. And then there are further more columns, other columns there. One of them would be for outcome, for the treatment, and stuff like that. And once you have the single flat table, under some very nice assumptions, you can do effect estimation using MALS, which is your favorite estimation method, right? Because it's interpretable and accurate. So you can use MALS on top of this Carl algorithm to estimate treatment effects. This is perfect because now it allows you to deal with some kind of relational data along with using an interpretable and accurate matching method. And so what do we find now? We find that the distribution of conditional average treatment has changed now because we are accounting for the neighbor's covariate. It more looks like a bacterian camel, right? There are 2 humps. There are some units which are less affected by the treatment, so they have lesser treatment effect, and there are some units which are clustered with high treatment effects. And this kind of makes us curious to ask, who are the units, or which are the units which have high treatment effect, and which are the units which have low treatment effect? And what's the natural thing to do? The natural thing to do is to go back to the match groups and look at the match groups which are on the left-hand side and on the right-hand side, right? So that's exactly what I did. I looked at the units which were on the left-hand side, and I found that these are the units who either already have a savings account, or most of the neighbors have savings account, right? So in some sense, they already know the financial institutions, and the financial institutions know them already. And hence, maybe participation doesn't really help them as much. While people who were really positively affected by participating in self-help groups were units who themselves did not have a savings account. Neither their neighbors had savings account. And this is interesting because it kind of highlights to us that self-help groups are highly effective to populations which are not yet introduced to banking system, who are not familiar with how things work, and banks do not trust them. So if you, as a policymaker, if you were to make decisions on where to encourage self-help groups, how to encourage self-help groups, you should primarily look at units who do not have savings account, and their social network also does not have savings account, right? And you can go there and encourage them to participate. And participating in self-help group on an average increases your propensity in such case by around 45 times the otherwise if you hadn't participated. So that's a huge increase in your chances. And that's where the 63% and 1.5% in my initial slide actually came from. I'm just going to pause here. Sorry, pause here for the questions.
Harsh, can you comment on sort of the differences in how we should interpret these values versus the values in the first graph you told us?
Right. So in this values, what we are specifically looking at, and it's a great question, what we are specifically looking at is if my treatment status changed while my neighbor's treatment status remains as it is. And I'm not considering interference in the sense my treatment choice is affecting my neighbor's outcome, and contagion in the sense my outcome is affecting my neighbor's outcome. I'm not considering those. I'm only considering if the pre-treatment covariates of my neighbors and my pre-treatment covariates work as confounders, right? And I'm looking at only the change in treatment, only in my treatment status change on my outcome. So keeping everything as it is, if I were to participate in self-help group, what would be my potential outcome compared to if I hadn't participated? While in the earlier one, because the units were independent of each other, there is no idea of changing of my neighbor's treatment status. My neighbor's treatment status is independent of mine, and also it is not going to affect my outcome. So this is what I call as conditional direct effect. Does that answer the question, Alex?
It does, yeah. I'm just trying to sort of connect. So essentially, you have an omitted variable in your first analysis. Right?
Yeah. We have
So,
a lot of unobserved confounders, if I were to say that, or unaccounted confounders in our first analysis, and so we had selection bias there.
right. So one way to account for it is to sort of say, I know the way in which I can summarize my neighbor's covariates. The other way is to say that I know that there's some correlation in the potential outcome distribution and try to work it backwards that way. So can you think sort of how to interpret what you've done as, can you back out what is the correlation between units who have similar needs for their neighbors or whatever?
Sorry, can you repeat the last part?
Could you think about it as something like a correlation for units who share neighbors?
Correlation in potential outcomes for units who share the neighbors.
Yeah.
Right. Yeah, because that in that way you will be accounting for the selection bias, right? Because of the neighbors, right? Yeah. And so
Okay, thanks.
the other way you can look at the whole procedure by turning it upside down is you do a kind of universal join of all the tables, and then now for each unit you have multiple rows because of this many-to-many relationship. So then you can do weighted collapsing or weighted group by, and those weights kind of come from the summary functions, and it would kind of construct the similar flight table. The only problem there is it's an extremely expensive process, both time-wise and space-wise. And so this kind of allows you to take care of that in an efficient and fast way. And also, it's kind of cute, a little algorithm. I love it. Sweet. So just because I'm a PhD student, I need to graduate. So this is my exit plan. I talked to you today about malls and car. The other work that I'm working with Sudeepa, Babak, and Alex is what if we allow interventions on relational skeleton, especially like relational ties, right? So if I add one more friend for unit U1, or if U1 was part of a triangle versus not part of a triangle, how do you look at such treatment effects? And that kind of stems from this, this inspiration for that stems from this triad literature in social psychology about how people behave when they're part of a closed group. So that's the causal effect estimation side that I'm working on with Sudeepa, Babak, Alex, Cynthia, and folks. The other side I'm super interested in is uncertainty quantification on top of the estimation procedure. So something that I'm working with Claire is how how can you account for uncertainty in the network sampling procedure itself? So there is a sampling procedure by which you observe the network. What if there is some missing values there, or what if there's some bias there? Can you quantify the uncertainty there using some procedure? That's sort of very interesting to me, because you never observe the full network, and hence you need to know those. Quantifying those uncertainty might be very useful. What I'm working with Eric, and this is super interesting to me, Eric and folks at Amazon, is can you somehow validate and tell which causal estimation method is working well, right? Because all of this causal estimation method works under some assumptions. And in real data, those assumptions might not be true. So here we are looking at synthetic control, which is one of the kind of estimation procedure, and seeing if we can give more informed guess about which of these estimation methods are doing good, and how you can take the estimates with a bit of pinch of salt. So that's my kind of future directions that I'm working on. I would like to thank all of my collaborators, committee members, advisors for kind of supporting me. And I really like the pictures over here, but if you do not like some of the pictures, just text me personally. But I really like all the pictures here, and they're like so beautiful. Thank you so much for kind of helping me through my research process and teaching me so much. Lastly, all the pictures that you saw in the background were clicked by me during my visit to villages in India, Jhabua and HD Kode in India. There was an exceptionally good experience, which motivated me to do my master's and then my PhD. So I want to thank nonprofits, Shivanga and Kram, for enabling my visits there and teaching me so much. Lastly, I want to thank my parents, my wife, and all my friends who have been supporting me through these challenging times and throughout my life. Thanks. That's it.
Wonderful. Okay, so how are we going to do this? I guess we open the floor up for questions, right, from everyone, I suppose. Is that right?
Yeah, we can do that. I'll be happy to take any questions from everyone, actually.
Okay, so let's open it up for everyone, and then we'll have we'll have to figure out what to do after that. I don't know.
Could you go back to the slide with the DAG, the grounded DAG?
Yeah, this one.
So is a good way to think about this as follows. Like I give you a relational database, background knowledge, and a causal query. And so suppose my relational database also contains some social network data, like who are my friends and whatnot. So is this essentially rolling out the entire DAG across the entire network?
Yeah, you can sort of think of that in that way, right? So I want to remind you of, so we kind of entered these rules, and this were with variables u and v, right? We did not explicitly say. So the skeleton traversal goes and maps these variables to the observed entities or relationships that we have. That's how the rolling out thing happens.
Right. So presumably this is a, I mean, my prior would be, this is a computationally expensive process. So intervening on the DAG, so if there is a change in the network structure, you would have to redo the entire process essentially, right?
So that's why we assume that the network structure is immutable, right? Right. So if we were to do interventions on relationships, for example, we would probably look at a slightly different procedure, and that's, I guess, work that I'm currently looking at to make it more efficient. So yeah, that's an extremely good question, though. How can you make it not expensive to recalculate all of these things?
Yeah, no, I'm just trying to understand what the grounded DAG exactly means. And does the grounded DAG change with what causal queries I want to ask?
No, so the DAG does not change. The highlighted edge over here changes, right? So if my question is my savings account affecting my loan status, right? Then you are looking at this particular edge as being red color. Also, you need to take into account this implicit temporal ordering, right? Because some of the things might be happening after the savings account has happened. So you should not condition on them. So you need to take into account the temporal ordering. I have conveniently omitted that here, but you need to look at that. So yeah, the DAG does not change. The causal query only changes which arrow is highlighted.
Right. So, I mean, if you keep on adding queries, it would scale better than changing the whole DAG.
Right. So you can ask
Okay.
multiple queries at the same point of time.
That was not obvious from the.
Right. Yeah. No, thanks for pointing that out. Yeah, that's a great question.
Other
Eric,
questions?
you
Oh,
had
go
a
ahead.
question, Eric.
Yeah, I do have a question. Really nice job, Harsh. Very interesting work. I had a question about the stretch. What is it called? Stretching before matching, or
Oh, matching after learning to stretch.
oh, matching after learning to stretch. Great name. How do you make inferences of after going through that exercise of figuring out the optimal direction to match? Because you do have to account for the uncertainty that comes from this first step, right? If I give you repeated samples, you end up getting different directions potentially just due to sampling variability.
Right.
And so have you given a little bit of thought about how you might construct valid inferences that account for that process?
Right. So maybe let me first answer the first part of it and then kind of look at the future direction. So the way I do it right now is conditional on the distance metric I learned. I assume that that distance metric that I learned is correct, and then I do the second part, which is the matching. And then because I repeat this process multiple times, each time I might get a slightly different distance metric. It would create different match groups and give me different K estimates. So that allows me to kind of think in the uncertainty that is existing in the process of learning distance metric and the limitation of finite data in some sense.
But it's a very so do you use all the data to match for each person? There's something
Yes,
that's a little
yes.
confusing because I see. So
I use all the estimation set to match, not the training set. All of the estimation set to match, and because we kind of repeat this process alpha times, some of the units which might be in the training set earlier might now be in your estimation set, and so there is a potential of those matches possible as well.
Okay. My concern is that matching is a very non-continuous operator.
I know.
And so these kind of resampling techniques will often break down, like the bootstrap, depending on what kind of matching you're doing. And so I wonder if you could maybe, I would be worried about maybe formally showing that this would actually give you correct inferences.
Right. So in the actual package that we've rolled out, we have got two options. One is hard matching, which is matching unit A with unit B, right? And the other is soft matching, where everyone is essentially matched with everyone, but the weight you're matched with is exponentially decreasing with distance, right? So e to the power minus t. And that's kind of soft matching setup. And so in that case, this kind of bootstrapping thing or kind of resampling thing, if I were to say that, allows you to average out the bias due to omitted units in the training set. But yeah, that's a good suggestion to kind of formally prove that that it doesn't introduce any bias in the estimation step.
Okay. And if I may, I had another question, and then I'll shut up and let other people ask questions. Which is, can you connect this maybe? So the whole idea of there's some notion of modeling here, right? You're doing it non-parametrically, but there's some notion of the scale on which your variables, your covariates are coded, And so do you have a notion of under what modeling assumptions are you actually getting a consistent estimator? Because this is not completely non-parametric. I could throw in some interactions you haven't matched on just because you happen not to have them coded in your data set. And it happens that they turn out to be highly predictive of the outcome and the treatment. And so do you have a sense of what modeling, what outcome model is this a reasonable, or will this yield a consistent estimate of the causal effect?
Yeah, that's a great question. So we have a theorem in the paper which talks about the consistency, and so the assumption that we make is of this smooth distance metric, which kind of loosely translates to saying if two units have similar x, then it implies that the y's are not further than delta. So if x's are close by epsilon, then they're not further by delta. And as you make epsilon smaller, the delta goes smaller, right? In expectation. So under that assumption, this works pretty fine. So for all kind of LP distances, this works okay. That's the assumption that we make for consistency.
Okay, thank you.
So how does that clash with having like binary covariates in your matching?
Sorry?
So this assumption would work nicely for continuous covariates, right? What
Right.
about the binary and the count type covariates that you have?
Right, that's an excellent question. So yeah, so that assumption breaks down in theory on binary covariates in the sense either they are exactly the same or they are very far away. That's how we see them in the binary covariate. So there is no idea of smoothness there. But in practice, it pretty much works because of this very fact, because you either think of them as exactly the same. So the epsilon is 0 or the epsilon is infinite. And so if the epsilon is infinite, then you allow your y's to be anything, and your epsilon is 0, then your y's are pretty close. That's the idea, if everything is binary. But in theory, it might break down. Does that answer the question, Ajinkya?
Right. Yeah. So you're saying if it's a point set topology, then the proof might just work, but you haven't actually proven.
Yeah, no, I haven't actually proven. And I mean, the primary motivation for this came from what if you have continuous covariates in a compact set? How do you deal with that? And then we kind of looked at the proofs around that scheme of things. But it works very efficiently even on the discrete covariates, which is kind of something that we have shown experimentally in our paper.
So Harsh, I've got a question. Well, first, very nice presentation. And my question is, I guess, is related to some of the things people have asked before, but I'm going to sort of turn the question around a little bit. So people have been asking, okay, what if this assumption is violated, or what happens if you do this? And let me ask the question another way. So if you were to imagine a sort of a pathological data set that would give you sort of the very worst performance with malts, what would that look like?
So one data set which malts does not work with very well is if your potential outcomes are like boxes, right? So potential outcome is 0 if your x, think about one-dimensional x, right? So if your potential outcome is 0 for 0 to 1, it suddenly is 1 for your values of x between 1 and 2, and then it's again 0 for all the other x's, and then you can kind of think of this this being scaled in like a high dimension. So it's kind of a box. So because malts has this smoothness kind of assumption on the outcome, this idea that if two x's are very close, then your y's are very close, it breaks down at the boundaries of this box pretty much. So that's one place where malts performs bad. Sorry, does that answer the question?
Thank you. Yes, thank you. That's a good answer. Thank you.
Harsh, I have a quick question. So can you comment on the uncertainty estimation for moles? Is it like the variance of all these repeats that you have written, alpha times beta?
Right. So ideally that should have been the case. That's exactly not what we are doing. So it's not very clear. So Vittorio had some ideas on why that's not, but let me tell you what we are doing. So we take all this K estimates for each unit that we get after this repeats, and then fit a smoothing model on top of it. So something like a Gaussian process on top of it. And then we take the variance estimated by that GP as the variance estimate that we give to the user. The initial idea was to kind of use this repeated values to somehow come up with this bootstrap kind of estimate, but it underestimates the variance in a lot of cases. And Vito suggested that it might be because there is a correlation between which units are in trainings, which units are in which split, and hence it kind of shrinks the variance compared to the true variance. So we still need to work a bit more on variance estimation. Currently, we're just by doing fitting a smooth model on top of the estimated kits and giving that variance as the estimated variance.
So, okay, so related to that question, so when you are repeating this alpha times beta times for each K estimate, so then what do you show to the user? Like there will be different match group for the same unit. So if you show that you could be either matched to these people or to this people, won't that be confusing? Like, is that practical?
So,
or your Kate could be either this value or that value, or so Kate still makes sense. You could show a distribution of Kate, but when you want to highlight interpretability, what do all these different match groups say?
Right. So that's an excellent question. So what we give as an output is sort of a sparse matrix where cell I, j in the sparse matrix corresponds to how many times unit J was in I's match group in all these repeats. And then you can kind of interpret either of that as weights, or the other way you can interpret is you can say that I only want to look at units which will match more than, let's say, 10 times with this unit. And that's my match group that I want to look at, because those are the units which contribute the most to my average Kate, right? So I have a lot of Kates and I give the output as the average Kate and the standard deviation of the Kate. Which units would contribute the most to my average Kate? Those were the units which are matched maximum number of times with me. And so we give this sparse matrix as an output, and also this idea of kind of thresholding it and seeing only those units when you're outputting a match group. So that's one way we are giving the output. The other thing we show is this weighted graph. So if unit I is matched with unit J, then you can think of that there is a directed edge over there, and the edge is basically weighted by how many times you got matched. So that's another representation that we give as an output in the mols package.
Okay, thanks.
Also, Harsh, you could just run this once and it still performs reasonably well.
Yeah, you can perform. You at least need to run this twice, because otherwise there is no way you can estimate variance.
Yeah, forget about the variances. You can do pretty well on K's.
Yes, absolutely. Absolutely.
I think that also goes to Eric's question, which you don't have to do repeats, which brings you back to a slightly more easy theory universe for matching.
I agree. So there is just one problem there. If you do this only once, so then there are some units which are in the training set for which you would not have estimates for Kates, or you won't have match groups. So I remember a bunch of people complained about that in the first version of review of this paper. I guess it's a fair complaint because data might be costly. So that's why at least doing a beta split repeat is interesting if you don't want to do the alpha repeats.
Okay, so I think just in the interest of time, we should maybe move to a private session. I don't know how to do that. without, I don't want to tell everybody to go away. Usually we have them like wait outside the door, but I don't know how else to do it other than to ask them to go. Unless you know how to create a fancy thing, Harsh, where you like a.
Let's see.
Yeah,
I do not know how to do that. I haven't explored that option.
Yeah.
You could make a breakout session.
How can I do that? Can anyone help me
No,
with
that's going to be so complicated. You know what? Maybe we should just politely say goodbye to everyone.
Yeah. Thanks everyone for joining for the presentation and for giving the feedback. It was amazing. Please write to me if you have any questions, and feel free to use our method and let us know how it performs.
And
Thanks.
Harsh will provide tech support for it. So
Absolutely.
all right. Bye, everybody.
You can also stop the recording.
Yeah. Yes, I
Yeah.
can stop the recording.
Thanks.